So today we are going to go through covalent bonding. So covalent bonding basically is going to be slightly different from the ionic bonding. Okay, okay. So covalent bonds here basically you know that they are formed by the sharing of electron. Okay, so comparing against your ionic is transfer of electrons. Yeah. So your covalent is sharing, so it's slightly different. Okay, and it's between atoms of non-metals. So covalent bond right occurs non-metal plus non-metal. Yeah. Whereas your ionic is metal plus non-metal. So metal plus non-metal, they can transfer because metal want to lose electron, non-metal want to gain electron. So they will just transfer across. But when you have a compound formed between two non-metals, both also want electron, right? Then cannot be one transfer and then one receive. So both of them will end up sharing. Okay, so just take note that for shared electrons, they are actually counted to both atoms to achieve that stable configuration of our gas. Okay, okay, so a single covalent bond, so take note of the word single here. Okay, one bond is formed between two atoms where each atom share one electron each. Yeah, one electron each. Means in total, there must be two electrons, one from each side of the atom. So let's say I have chlorine and chlorine. So chlorine exists as Cl2 because your chlorine has 7 electrons. Right? Okay, and then let's say the other one is X. 5, 6, 7, like that. So what they're going to do is each of the chlorine will share one electron each. Okay, so that it looks a bit like this. I'm going to draw the chlorine like this. Okay, so the X electron is in the middle. Then the other one, this one will have 6 left of its own electrons. This one also 6 left of its own electrons. So what I mean by shared electrons are counted to both, right? It's like you see these two here are being shared. Okay, these two. Okay, so this side, this chlorine has 8 electrons because you have 1, 2, 3, 4, 5, 6. This one also counted 7, 8. Then the other side chlorine also has 8 electrons. So once it has 8, then the shell is full, then they are stable already. Okay. Okay, where got one new student coming in. And hello. Hi Harini. Can give me a thumbs up if you can hear me.
Yep, I can.
Can hear. Okay, okay. So actually, I started a little bit ahead lah, because we are just doing a little bit of a recap for covalent bonding. Then later I will go into going through all the questions. Okay, if there anything, any questions, you just ask, no problem. Yeah, we learn together. Okay, okay. So we covered so far that covalent bonding basically is about sharing of electrons. Okay, so over here, sharing of electrons allow the non-metals to reach stable electronic configuration. So you want to have 8 valence electrons. Okay. Uh, okay, so the moment you share 2 electrons, this is known as a single covalent bond. So it is one pair of electrons. One pair of electrons. Okay, so as I go more and more, if they share more and more electrons, like for example, sharing 2 pairs of electrons, that will be known as a double covalent bond. Okay, if they're sharing 2 pairs, means each atom put in 2 electrons. So it will look something like this. I draw on the left side, it will look something like this. That means you will have 2 pairs of electrons. Okay, then triple covalent is when you have 3 pairs of electrons. So let's go through an example. So why fluorine exists as F2 is because fluorine, right? If you go and check out, is element number 9, yeah, atomic number 9. So it means that each fluorine atom has 9 electrons. So for 9 electrons, how they arrange the electrons will be 2 in the first shell and 7 in the second shell. And this is the valence shell, the outermost shell. So this is not stable because it doesn't have 8 electrons, which makes it full. So each fluorine needs one more, right, to make it 8. They want to achieve this 2, 8, where this thing is full. So as an element by itself, right, remember for element, it is only able to interact with itself. It should only be one half atom. So it can only bond with other F atoms. So this one, F is a non-metal, right? So between F and F, this is non-metal. plus non-metal. I should form the NM means non-metal. Okay, so this one means that the bond is covalent. Okay, not ionic. Ionic is metal plus non-metal. Okay, so let's look at the diagram below. What happens is basically your fluorine has 7 valence electron. There is one here for each of them. Then they're just going to share it. So when they share, we're going to draw their orbitals overlapping. The electron shell will overlap. So there is overlapping area here. Okay, then each of them will put one in. And it will never be a case where one guy donate more electrons than the other. It's always equal on both sides. So it is one in, the other one must also put one in. Okay, so over here, you'll realize that after they form this single bond, this is a single bond because you only share one pair of electrons. Okay, so single bond. Okay, you count the valence electrons. For the left side, you have 1, 2, 3, 4, 5, 6, and then you must count the shared ones together also, so 7, 8. Okay, so for the left side, it is full already. Then the right side is 1, 2, 3, 4, 5, 6, and then 7, 8 here also. I ignore the inside because the inner two are not considered valence electrons. Okay, so this is how they form the F2, and that's why they exist as F2 diatomic molecule. Okay, so basically this is what I explained. Okay, only one electron to form a single covalent bond, then it will have this structural formula here. You will realize that there's a line in between. So this single line in between represents a single covalent bond. Yeah. Okay. So yeah, let's have another example. So we look at oxygen also. So why oxygen exists in O2? Okay, similarly, your oxygen is atomic number 8. So it has 8 electrons per every oxygen atom. So the electronic configuration is 2, 6. So it has 6 valence electrons. Okay. That's a topic. And that is 5 valence. Okay, so it has six electrons. And then when we functioning, we are really trying to figure out what's going on. Okay, I try and use my cursor. Can you see the cursor on the slides? And
Yeah.
okay. And so for oxygen's case, each of them need 2 more electrons because they only have 6 valence electrons. Yeah. So instead of sharing one only, if you realize that if they share one only, then they will only have 7 electrons each. So they will share 2 instead of 1 electron each. Okay, so they are sharing 2 pairs instead. Okay, so each oxygen 6 valence electron, put 2 inside, they only have 4 left for themselves. Yeah, such that in this case, your left side over here for oxygen, there's 1, 2, 3, 4, 5, 6, 7, 8 valence. The same for the other one as well. Okay. So this one is what we call a double covalent bond because they're sharing 2 pairs of electrons. And you see the structural formula here, this is a double bond. So it's a 2 lines instead of a single line. Yeah. So if it's a triple bond, then it will be 3 horizontal lines. Yeah. Okay. So in terms of covalent compounds, right, unfortunately, it's a lot more complicated than your ionic compounds. Where ionic compounds, they only have one type. It's one type of structure. Your covalent compound has 3 types of different structure. Okay, so there's simple covalent, giant covalent, and macromolecules. Need to know what is the difference between all of them also. Okay, so when the compound exists as discrete molecules, they are known as simple covalent. So discrete means, right, you can separate one molecule from the other one. So things like a water, you know that water is confirmed going to be H2O, H2O, H2O. It doesn't form like a very, very big structure. It's just a simple H2O. So if you're able to separate these 2 molecules out, this is called simple covalent. Okay, later you see the structure of others that is not simple covalent. Then you know the difference already. Okay, so things like carbon dioxide and ammonia, all these are all simple because you can see here very clearly one molecule, one molecule, one molecule, one molecule. Okay. When your compound actually forms a giant network of atoms and bonds, so these are known as your giant covalent molecules. So you can see it's very clearly. I cannot see where is one molecule. This is like, you just imagine it's a very huge branching of your atoms and bonds. So over here, right, you just need to memorize. It is a memory work. You need to memorize. I got 3 of them that exhibit giant covalent structure, which are your diamond, graphite, and sand. So diamond is this one over here, graphite is here, sand is this one. Yeah. Later we'll go more in detail about these kind of structures also. Okay. And then macromolecules is basically when you have a lot of molecules of your simple covalent, right? Not all of them have this property, but some of them are, when you link them up together, right, they can form a long, long chain. So for example, some simple covalent molecule like, okay, CO2 is a bad example, but let's say it's CO2. A lot of the CO2 can come together and bond, form one very long chain. This long chain is known as your macromolecule. Okay, so it looks like this. The chains that they form can be very random one. It can be a straight chain, it can be branch one, it can be anyhow. Lah. Okay, so this one is your macromolecule. Okay. Okay, so understanding the structure, then we can go into the properties also. Lah. Okay, so for simple covalent molecules is the one that you have one molecule, all separate from one another, right? Okay, you need to understand that your simple covalent molecules, they are held together by weak intermolecular force of attraction. Yeah. So this is in contrast to your ionic. Ionic is strong electrostatic forces of attraction, which means it is attraction between your plus charge and your minus charge. Here you don't have plus and minus charge. All of them, they don't have charge particles, man. They are only sharing electrons, right? So when they come close to one another, then they start to attract each other, and this attraction is weak. Okay. But don't be mistaken, because a lot of students will think that, oh, because it's weak force of attraction, right, then the covalent bond is weak. But this is a mistake. Actually, covalent bonds are very, very, very strong. Okay, so a diagram here maybe can help you to visualize what I'm talking about. Intermolecular force of attraction, right, comes from the word inter, means between, and molecular means molecule. So the attraction is between molecules. So you have, let's say, water molecule, right, one here, and one here. The intermolecular forces is in between the molecule, is the dotted line outside one. When they come close to one another, then they attract each other. This is the attraction. So these are the weak attraction forces. Whereas for covalent bond, remember, this is the overlap. This is the overlap of your electron shell when they are sharing the electrons. So this is going to occur inside the molecule between, let's say, the hydrogen and the oxygen. So you see the line here, this one is like just imagine it's the covalent bond between the H and the O. So this one is strong. Yeah. Okay. So one of the properties of simple covalent molecules is that they have low melting and boiling points. For your ionic is high because their electrostatic attraction is strong. You need a lot of energy to overcome. Right? So a lot of energy means you need to have high melting and boiling point. For simple molecule, right, we go back to this diagram here, right? Let's say water molecule. If you want to melt the ice to become water, or you want to boil water to make it into steam, what you're actually trying to overcome, right, is actually the intermolecular force of attraction. You just need to let them slide past one another, or you let the molecules be free from one another, not attracted anymore. You are not actually trying to break the covalent bond and form the different atoms, right? So you're not trying to break covalent bond, you only need to overcome this weak attraction only. That's why, right, the energy required to melt and boil is actually not very much. It's very little. Okay, so because of this, your small amount of energy is required, and that's why melting and boiling points are lower. And because of this property, then most of your simple covalent substances at room temperature, they are usually gases, like oxygen gas, nitrogen gas, carbon dioxide, then or liquids are like water. Okay. So either gases or liquids. Okay. So just to share with you a bit, okay, volatile here, right? Volatile means what? It means something that can evaporate very easily. So an example of a volatile liquid would be things like ethanol. Whatever you use to disinfect your table, you realize after you try and clean up the table, then it dries up very fast. The one is volatile. Okay. So in general, for your covalent compounds, okay, the melting and boiling point will increase if the mass of the molecule increase. So let's say I'm looking at water versus carbon dioxide. Or maybe, okay, not a very good example. Maybe, okay, carbon dioxide versus a very large molecule, like maybe the macromolecule, right? So macromolecule, that kind, right, will have a much higher boiling point compared to carbon dioxide, because carbon dioxide is very small. Okay, so small size, usually NP and EP will be lower. Larger size, usually NP and EP will be higher. So this is only for covalent, not for ionic. Okay. So same thing as I mentioned just now, note that the covalent bonds are not broken. So do not ever explain it as in order to melt covalent, you need to break the covalent bond for simple covalent. Then that one will be 0 marks already. Okay, it's overcome intermolecular forces of attraction. Okay, in terms of solubility for ionic, last time we learned, right, it is soluble in water but not soluble in organic solvent.